Welcome back to Module 3. So far in this course we've looked at using the select statement to query tables in our SQL Server database, and Jeff, you've talked us through doing some fairly advanced select techniques using ordering by and using the where clause to filter the rows that were coming back. So we're getting to the point now where we're writing some queries that bring back the data that we want from one table. But as I said right at the beginning of the course, actually most databases have multiple tables. So let's take a look at querying multiple tables with joins in this module. What we're going to cover, there's a number of things to get through. We'll talk about some basic concepts of what a join is and how they work. And then we'll look at the syntax that we use to define joins in our queries that join together data from one table to another. And then we'll look at 4 different types of join that we can implement in Transact-SQL and understand the differences between each of those and when we would use each of them. So I want to start off with some basic join concepts. Now, Jeff, you've worked with databases for many years. You'll kind of know about this.
Never with more than one table, though.
Never more than one table. Oh well, okay. You can leave for the rest of the course then. So. It's actually fairly common. I mean, in most cases, sometimes you'll query one table, but actually it's pretty common to be bringing together data from multiple tables. And what you're doing is combining the rows by matching using some sort of criteria to match rows in one table to rows to another. So we're not querying one table and then querying another and then just sticking the results together as one result set. There are times when we will do that, and we'll talk about that in a later module. But here, what we're talking about here is matching rows in one table with corresponding rows in another table and mixing them together. So it's usually based, not always, but usually based on a relationship between a primary key and a foreign key. You might remember at the beginning of the course, I talked about a primary key as being the thing that uniquely identifies a row in a particular table. So give me an example of a primary key.
An order ID or a customer ID. They often end in ID, to be honest.
Yes, that's true. Yeah. So usually sometimes a primary key could be multiple columns. It could be a composite key, like an order and line item might together make a unique identifier. But more often than not, in tables that represent business entities, you have a unique value that identifies that. That's the primary key. When you have another table that references that thing. So let's say the thing is a customer. We have a customer ID that's the primary key for customer. In an order table, a sales order table, I don't want to have the customer's name or the customer's address or all that detail in there. I just want to say this customer over in the customer table. And so what I do is I put the customer key. And in that case, it's called a foreign key because it's not uniquely identifying the sales order. It's the key that uniquely identifies the customer for the sales order. So we have this primary key, foreign key relationships. That's not the only thing we can join on, but it's the most common. And an example on the slide there is returning rows that combine data from the employee and sales order table. You might have employees. If you're a sales organization, some of your employees will be salespeople, and you want to figure out which are the orders that salesperson is responsible for selling. And we match it based on the employee ID relationship. Now, it can be useful when you are thinking about sets of data. Remember, right at the beginning we said that a lot of the things we'll do in Transact-SQL is based on set-based theory or set theory in mathematics. It's useful, especially when you're thinking about joins, to think of things in terms of Venn diagrams, collections of things. So in this case, we have a collection of employees and we have a collection of sales orders. And where those two sets overlap, where they intersect, we've got the sales orders that were taken by employees.
So any employees who haven't sold anything,
they won't be in that set, in that join, by default. We will talk about different ways of creating joins, but think of Venn diagrams. It's a really useful way to kind of visualize in your head how you're joining things together. And as you'll see as we progress through the module, it will help you figure out which types of joins you're trying to define. So let's look at the syntax that we would use when we're working on this in Transact-SQL. And there's actually two variants of how we can do this, 2 ways that you can express joins. In 92, the ANSI standard for making joins was actually to do it in this join operator in the from clause. We created a standard. In the from clause, we have the join keyword, and there's other keywords that go with that, which we'll talk about in a minute. But basically, we're saying select whatever from this table, join this other table on, and then whatever it is that we're using to join them, whatever the predicate is. So we're explicitly joining in the from clause. There is an older syntax that was a standard for a while, where we did it in the where clause. We saw the where clause in the previous module. It's used to filter rows. Well, you can think of a join as being something that filters rows. It's filtering rows where there's a match between the two tables. So you will find code out there where the join is done in the where clause. My recommendation to you, and I'm sure you would agree, Jeff, is that's probably not the best place to do it.
No, I mean, as you'll see Cartesian products later on, intentional Cartesian products, but we don't want accidental ones. The sad thing is that we're both old enough to remember when SQL 2 was the new thing.
That's right, yeah, I remember that was the new syntax. So we really want to avoid using the older syntax, avoid doing the join in the where clause, try and use a join, explicitly a join statement in the from clause. Cartesian products has been mentioned there. And since you mentioned it, Jeff, I'll give you the honour. What's a Cartesian product?
So, I don't know where the name comes from, because I think of it meaning some sort of well in ancient times.
It's artisan, isn't it?
Artisan, is that? Well, I thought that was a type of product, a delicatessen. But anyway.
Okay.
Cartesian products basically saying every combination. So I'm not interested in employees and their sales. If I do a Cartesian product, I have every employee against every single order. So every single combination. Now, it could be that that's a useful thing. It almost certainly isn't a useful thing. The only relevant example I ever come up with tends to be if you have a thing at work and they assess you in various categories, and they say, okay, your skills at management are this, skills at sales are this, and you get a number. And then we have all the roles in our company, and we say, well, this is the required skill level in these different categories for this role. Then what we could do is search our employees to find any employee that meets the requirements for a role that's become available. So to do that, I want to do every combination of roles available and employees, and then filter it to say I'm only interested if the employee has a greater or equal to value than the requirement in the job.
So you're matching every employee to every role and then filter
to do
it.
every single.
Right.
But
Okay.
it's quite unusual that you do want to do it.
The only other one I can think of is if you have a table of, say, soccer teams, and you're trying to arrange a tournament where every team plays every other team, in that case, you do a Cartesian join that's actually a self-join on the one table, which we'll get to in a short while, where we get every possible combination. And in fact, you would get home and away because it would have combinations that work in both directions. So Cartesian products, it's a shorthand way of saying every possible combination of the records, and the reality is, apart from these fairly esoteric examples, it's generally not something you want. It's very easy to get them accidentally if you use a where clause to define your join, whereas the join keyword in the from clause is much more explicit, and it's easier to avoid getting these Cartesian products. So I talked about different types of join. We talked there, I mentioned a self-join. We'll talk about other types of join later on. But the first one, the most common type of join that people want to deal with or start with, is what we call an inner join. And again, we want to think back to the idea of the Venn diagram. So we're returning rows where only rows where a match is found in both tables. So where there's an employee that matches a sale. I might have sales that don't have employees attached to them because I might have a store where customers just take things off the shelf and there isn't a salesperson involved. Or I might have employees who've never sold something, and I'm not interested in any of them. I'm only interested in when an employee comes together with a sales order. So the way to think of that, as I said, if you think about this conceptualized idea as a Venn diagram, that looks like that then. An inner join is the bit where the overlapping area is where I'm finding the equality. So I've got an employee and a sales order, and both of those things exist. When we do it using an equal or an equality predicate, which is most of the time, if I'm honest, you'll occasionally see it referred to as an equijoin. And some people use the terms interchangeably. You've got to be quite careful. Explicitly, an equijoin is when we're checking on equality. An inner join is any case where the thing is in both tables.
But I think you tend to, if it's not equal to, you would make it clear.
Yes.
Because by default, virtually everyone you see will be equal to. So.
Yeah, exactly. So so that's an inner join that we've got an example there. You can see the code example. We're taking the first name and the order amount. Notice that because I'm getting from two tables, now previously we've used aliases for columns. Here I'm using aliases for the tables as well. So I could have column aliases and table aliases. And the advantage of having the table alias is I can then explicitly say which table a column comes from. So in this case, emp.firstname means the first name column from the employee table, and the amount order from the order table from employees, which is joined to the sales order detail table. Now you'll notice I've put the inner in square brackets there. And that's because, like much of SQL, we've talked about this before, the inner is actually optional. If I just put join, then SQL Server or Azure SQL Database knows that that means an inner join, right? So I don't need to specify inner. I usually do, when I'm writing Transact-SQL, I usually do just because I like to be explicit about what type of joins I'm creating. So I tend to be as explicit as I can, but you don't have to. You could just say from employee join order.
And what if you had another table as well? Could you add to that and say, well, actually, I'd like some information about the customer as well?
Yeah, I could join on multiple tables and just keep having additional join clauses for all the tables that I want. It gets a little more interesting when I have different types of join, and we'll see that in a little while. But assuming they were all inner joins, I just keep adding join, 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 and then the second part of the join clause is on, and what it is that I'm using to match the two tables. So in this case, joining it where the employee ID and the employee ID are the same in the two tables. So that's the syntax. Let's look at a demo of how we can create some inner joins. So I'm back in SQL Server Management Studio, and I've got some code here that I want to use to create some joins. And the first one I'm doing is I want to get some information about products and the categories that I'm using to categorize them. And in the database, I've actually got a product table and a separate category table. So I'm storing information about the categories separately from the products. And I'm joining them on a common key. The category table has a primary key called product category ID, and I'm using that as a foreign key in the product table to say which category a product belongs to. So let's look at the syntax, and I've not used any aliases for the tables here. So select from the sales LT schema, the product table, the name column. So I'm getting very explicit in terms of what I want to get out of there. The name column from that table and the name column from the product category table. Now the columns have the same name, and if I didn't alias the columns, as I've done here, then I would end up with two columns in the result set both called name, which would be confusing. So I want the product name as product name and the product category name as category. From the product table, inner join, and the inner is optional, but I've put it in there, the product category table, where the product category ID in the product table is the same as the product category ID in the product category table. So it's a bit of a kind of mouthful to work your way through the syntax, but if I run that, what we should get is an error because I'm not in the right database. And we'll switch it to the right database. And then what we'll get is a list of product names and the category that those products belong to. And if I scroll through the results, you can see there's different types of product, and I can see what they are. So the business of having to explicitly specify the schema and the table and the column becomes a little cumbersome when you're dealing with joins. It can be quite confusing in the syntax. So usually what you do, as well as using column aliases, as we've done here for the name columns, product name and category, we also use aliases for the table. And quite often, because these aren't visible in the results, they don't show up as column titles or whatever, you'll see a lot of developers just use something simple, like the first letter is quite common. Sometimes you might be more explicit. If you've got lots of tables, you kind of want to use something that's immediately intuitive as that table. But in this case, I'm saying P is the product table, C is the product category table. So that's a much simpler version of exactly the same query that we just executed, this time just using an alias to represent the name of the table. So what if I've got multiple tables? Now, we've got our products in our different categories, and we can see the relationship between product and product category. We've also got products that are sold. But actually, what happens is in a sale, there's a sales order, and then the sales order has line items. So over here in my list of tables, I can see there's a sales order header table, which has all of the columns to do with at the sales header level, and I could list those out there. There's a lot of them just at the header level. But then for each order, there could be multiple sales items. So there's also an order detail table. And the order detail table has all of the things relating to the individual line items that make up that order. And one of those is the product product ID. That's the foreign key to the product table, which has all the details for the product. So there's 3 tables involved in getting a list of products that have been sold, because I want to get the order level details, the order date. I also want to get the individual line item, like the number of the product that were ordered, the quantity, and then I want to get the product details. So let's take a look at the query. We've got from the order header table, I've aliased that, get me the order date and the sales order number. And then I'm joining the sales order detail table, calling it OD, because from there I want to get the quantity and the unit price and the line total. And I'm also joining the product table, which I'm calling P, because from there I want to get the product name. So there's 3 tables there. I just simply join them all on one after the other. The order actually is unimportant in this instance. It doesn't matter what order I put them in there. And notice I've missed out the inner. I've just said join, and by default that will be an inner join. So I'm doing that, and then I've got my order by at the end, where I'm doing an order by clause as well.
So if you didn't want things from that middle table, so you wanted some of the order details, and you wanted some of the product information, but the order header table didn't have any data you wanted, would you still join that one? You'd
still have to join it. You'd admit it out in the select. You'd admit it in the select statement. But remember the order that things get done in. The from is the first thing. So at the point where I'm defining my joins, I'm not really worrying about the columns I'm going to ultimately select. What I'm doing is defining the kind of master row set, the virtual table, from which I'm eventually going to select some columns. Okay. And if that includes a join, then the join has to be there all the way around. The other thing that's interesting, we talked about Cartesian products earlier on. Internally, the way this works is that what SQL Server will do is initially do a Cartesian product and then filter out based on the predicates and the joins that I've defined. So under the covers, Cartesian joins are used. It's just generally that's not the result we want. So if I go ahead and run that, it's bringing me back data. The order date and the sales order number came from the order header table. The product name came from the product table. And the quantity, unit price, and line total came from the order detail table. So I've got multiple tables being joined. Now there's one other thing to mention here as well that's worth making a note. We've joined our tables in this query here. We've joined the sales order details table to the sales order headers table based on a common key, the sales order ID. And similarly, we've joined the product table based on the product ID being the same. So there's one thing that joins those 2 tables. The on part of a join is a bit like a where clause. You could have multiple things like ands and ors and all that type of thing. So we've actually got here an example where I've said, bring me back all of the sales where the product ID is the same as the product ID. So all the sales for that product. And the unit price that I sold it at is the same as the list price for the product. So I've got a list price in my list of products, which is the price I want to sell it at. And what I'm doing is bring me back all the times when I sold this product at the price that I originally wanted to sell it at. So there's an and clause in the on part of the join.
So you said that you could have a 2-part primary key. So if you had a 2-part primary key, then you'd be using a join on multiple columns.
Yes, yeah, and again, you would do the same thing as I've done here. So interestingly, you'll notice that in our data set, if I run that, we have never at any point sold a product at the price we wanted to sell it for. So it's a safe bet we've been discounting. So we'll change our clause to a less than there. And sure enough, there are our orders. So sometimes by adding that additional clause in the on part of the join statement, you're able to add additional filtering criteria as the query engine assembles that row set that we're going to get the columns from.
Could we put that in a where as well?
We could have put that in a where. Because it's specific to the way I want to join the tables, I've put it in the and. Sometimes you could put it in the and. I've put it in the join. Sometimes you could put it in the join. Sometimes you could put it in the where. Sometimes it has to be in one or the other, depending on what it is that you're joining. Okay, so we've looked at inner joins. Let's talk a little bit about outer joins. And an outer join is when we return all the rows from one table and any matching rows from the second table. But from the first table, I want all of the rows, regardless of whether they're matching or not. So an example of this might be where I've got employees and orders, and I want a list of all the employees, and for the ones who've taken orders, I want details of the orders that they've taken. Now what happens here is, I said earlier on that what SQL Server does is actually create a Cartesian product before it filters out the results in the join. So in this case, what it does is create that Cartesian product and preserve all of the ones from whichever table it is that I've said is the outer table, and then filters out the ones that don't match in the inner table. So that's kind of the way it works. And you specify an outer join using left, right, or full. And in this case, the order in which I specify the tables does kind of matter, because if it's a left outer join, then I'm going to retain all of the rows from the first table I mentioned, the one that's on the left of the statement. If I'm specifying the right outer join, then I'm keeping all of the rows from the table on the right. And if I use a full outer join, I'm keeping the rows from both of those tables. Full outer joins are pretty unusual. You don't commonly use them. But what you might use it for is if you wanted to get all of the customers and all of the products, and where you had sold, not all the customers, all of the employees and all of the products, and where you had sold things, you'd want to indicate that they'd been sold, but you'd still want products that hadn't been sold, and you'd still want employees that hadn't sold anything. So you get that full result set. So matches from the other table, the table that's not the left or right of the outer table that we defined, are retrieved. Additional rows are added to the results for any non-match rows. So if I've got employees that I've brought back as an outer table and sales as the inner table, and there are employees who haven't had any sales, then any of the columns that are going to be brought back from the sales table, of course there aren't any matching columns for those in the employees, so we get nulls for those. So basically nulls, when you're working with joins, indicate either that there were nulls in the underlying data, or they indicate that this is from an outer table that doesn't have a matching inner table. So we've nulled out any of the columns from the corresponding inner table. I said beginning of we talked about joins, it's useful to conceptualize these as Venn diagrams, and especially when you're working with outer joins, it's useful to think of it as being like a Venn diagram, a set diagram that shows, here's my outer join that joins employees to sales orders, but I want all of the employees, regardless of whether they've sold any products or not. So my left outer join, and you'll see that the outer is optional. You don't have to specify the outer. I've put it in there just for fullness.
Because if you're putting left or right, then it's outer, whatever.
Yes, if I put left join, then it knows it's an outer join. So I've left joined the order table to the employee table, and because employees mentioned first, it's the one on the left. So I'm going to have all of the employees and the sales orders that match. And where the sales orders don't match, I'm going to get null values for the columns that come from that table. Let's see a demo of an outer join and see how that works. So in this case, I'm taking the first and last name from the customers table, which I'm left outer joining to the sales order header table. So I'm bringing back customers who have bought something and customers who have never bought something, which might sound a bit odd. How would they be a customer? In this case, in the sample data that we've got, we have customers who've perhaps registered with us. We sell to retailers, so retail companies may have signed up with us, but not placed any orders yet, and I want them to be included. So I'm bringing those back. I'm left outer joining on the customer ID equaling the order header ID. So let's run that. And once again, I'm in the wrong database, so we'll do that. You can see how easy it is to do that. So you can see I'm bringing it back, and I've got a bunch of customers with no corresponding sales orders. So these will be from my left outer join. I'm getting them from the customers table, but they haven't placed any sales orders. And if I scroll down through the result sets, well, there's a few popping in here and there. I can see a customer there who has placed an order. So I'm getting the ones that match and all of the customers that don't match. I am, in this case, getting any orders that don't have customers, which logically wouldn't make sense in this context anyway. But it's a left outer. So the only table where I'm getting all the rows from is the employees table, and I'm getting rows from the customers table where there's a match. So one of the useful things you can do with outer joins is actually check for the null values that get returned. So if I wanted to find a list of the customers who haven't bought anything, all I do is I append an additional where clause onto that query that says where the sales order number is null. I know that every sales order has a sales order number. It's a non-nullable column. So the only way it would be null would be if there was a customer without any corresponding sales. And if I run that, what I get is 815 rows. So I have 815 customers who've never bought anything from me. Clearly, there's some work to be done on the sales side of the business there. Now, it gets a bit more interesting if I have multiple tables that I want to join using outer joins. So you can see here that I want to get the product name and the sales order number from the product table, left join to the order detail table, which is where that product information is stored, which in turn is going to be joined to the sales order header table. Now, if I think about this logically, I'm not going to have any order details that don't have order headers. So you would think, well, that should just be an inner join. But I can't make it an inner join because of the way that the result set is actually formulated. What you get is initially a Cartesian join, and then we're filtering rows out that don't match. And because I've got a left join here, in that first one, the next table that I join onto the right of my chain of tables is going to have to join onto a table that may contain nulls, because the result of that first join is a left join. And I don't want to filter out the rows that have got nulls, because that was the whole point of having the left join. I want to have the products that haven't been sold. So once you've declared a left join or a right join, if you then continue to add tables onto the chain of tables, so if you've got a left join and then you add another table to the right, you have to keep using left joins, is basically the rule. So in this case, I've got a left join to join on join the order detail table to the product table, and then another left join to join the order header to the product table, so that I retain those nulls that indicate products that haven't been sold.
So quickly drawing out a Venn diagram would help you decide maybe which one?
Yeah.
It would help me decide.
Right, yeah. So if you think about that in a Venn diagram, that would help you to figure out which order your tables are in and whether you need to keep the left or the right.
Because it's possible you might do an inner join in the second one, I guess, but unlikely.
Yeah. Yes. Well, if you did an inner join, you'd lose all the products that you'd never sold.
Yes.
So if we run that, you can see that I get my products there that I've never sold. There's no sales order number for those, but I continue to get my details of the products that I have sold. So I'm getting from the product table here and the sales order number here. And earlier on, you asked about what if that middle table I didn't want any columns from? Well, it still had to be joined because it's necessary to get from products to order details to go through it's necessary to get from products to orders to go through an order detail. I'm just not bringing back any columns from there.
Yeah.
So here's another example that has multiple tables, but this time the order of the tables is different. I'm selecting from the product table. I'm left outer joining the order detail table because I want products that I've never sold. And I'm left outer joining again to the order header table because I want the order number. And I'm having to use a left outer join because I'm continuing to add tables to the right of where I started a left outer join. But then I'm inner joining the product category, and it's because I'm joining that back to the first table again, back to the product category table. So, back to the product table, P. So because I'm joining that back to the first one I started with, if you think about these tables as being in order from left to right, this one goes back again at the very beginning of the chain, back to the left. So it's before the outer joins, so I can use an inner join. And this is where the syntax gets confusing. Whether you need to continue using an outer join depends on which side of the list of current tables are you adding this new table.
So it might be nice to reorder the...
Yeah, and I could reorder the joins to do it differently. Yeah, I could inner join that one first and then do the left outers later. But it kind of makes the point that sometimes you'll find yourself writing a query and logically you know that there's no way they're going to be non-matching rows, so you might as well use an inner join. But because you've already used an outer join and this one's being added to the right or left of that join, you'll have to use another outer join. If I run that, and you can see that it works. I get the product name and the category. That was an inner join between products and categories, and then a couple of outer joins to get me to the sales order number. And I can see that for my road frames here, I haven't sold any, but for the other products that are listed there, I have. So we've looked at inner joins, and we've looked at outer joins, a couple of different types of join there. The other type of join we're going to look at is cross joins, and you alluded to this earlier on, Jeff. We talked about Cartesian products.
Yeah.
And that's exactly what cross joins are designed to do. So we combine each row from the first table with each row from the second table. And we get all possible combinations back out of that. So here's an example where I've got employees and products, And as I run the query, there are the cross joins. Notice there's no on clause because cross join, you don't filter. You're basically saying cross join everything. So I don't need to have an on clause. I've cross joined my employee tables and products table. And what I get is every possible employee with every possible product, which is probably not something I would generally do. But there, as we said earlier, there may be occasions when you might want to get that type of result.
And this is a bit nicer than the SQL 89 syntax because it's explicit. You said, I typed the word cross, I know what I'm doing.
Yeah, and again, that's why we want to use that more modern syntax. If we use the older syntax, it's easy to do this accidentally. So this is actually the logical foundation for inner and outer joins. This is actually how SQL Server does things under the covers. It starts with a Cartesian product and then filters to get an inner join. And it starts with a Cartesian product, filters, and then adds back non-matching null rows to get an outer join. So actually, fundamentally, all joins are Cartesian products, but then they're filtered. Cross joins are just Cartesian products without any filters applied. And as we said, they're typically not useful. We've come up with a couple of examples. One was the matching employees to roles, so I want to compare every employee to every role and see if they've got the skills for those roles. The other is if you were generating a league of matches between two different types of team, you might have a cross join to get every possible combination there. And the other time I've seen it used is just to generate test data, where you take a list of random first names and last names and then generate every possible combination to give you some.
I'll be honest, that's the only time I've seen it used in anger.
In anger, is to generate test data.
The other ones are making up scenarios for training courses.
So yeah, it's pretty unusual that you'll use one of these, but it's good to be aware of the cross-join syntax.
Well, as you say, generating test data is something you need to do.
Yeah, absolutely. Let's look at an example of using cross-joins to generate every possible combination. And we'll just switch across to this one, and I'll remember to change the database context this time. And it's one very simple example. What I'm doing is getting the product name and the first and last name of each customer and the customer's phone number. And the scenario for this is a highly realistic scenario. I have telesales operatives who are going to phone every customer and ask them if they want to buy a product, and they're going to do that for every product. So it's perhaps not the most realistic example, or it would be very annoying if they did. But for each product, I've got every single product and every single customer, and then I'm going to phone the customer and ask them if they want to buy that product. So that's a cross join. It is every single possible combination. If we have a look down this, actually the query is still executing, you can see, because we have so many possible combinations, it's going to carry on executing until it gets them all. So even though I scroll down and I can see there's already quite a substantial number of rows, it's continuing to execute to get those back. And that's another reason you want to avoid accidentally cross-joining things, because it brings back a huge volume of data. If you think about how big each table is, it's then a factor of that can tell you how many possible combinations there are. It's finally executed with 249,865 rows returned. Okay, so self-joins. Let's finish off our discussion of joins with the final type of join, which is a self-join. And what we're doing here, as the name suggests, is we're comparing rows in a table to other rows in the same table. And there's the kind of archetypal example of this, where we do it. We obviously need two instances of the same table. And the example that almost everybody uses when they talk about this is this one here, probably because it's the most common way that you would do this. If you have a table of employees, and one of the fields for each employee is the ID of their manager. Well, managers are also employees, so you're effectively creating a self-reference. And what we would do is use a self-join to join the employees to their managers. And the way that we do that is we have, in this case, the employee first name as employee and manager first name as manager from the HR employee table as emp, left join to the same table again, but with a different alias.
So you need to use aliases here.
You have to use aliases because you've got the same table twice. Let's see an example of how we might use a self-join to join data in one table to another, or one table to itself, rather. What I'm going to do, because in the database that we've got, in the sample database, there isn't an employee table, so I'm going to do a little bit of work first of all. So don't worry too much about the syntax, but first thing I'm doing is...
change your context though.
Oh yes, good point. Change myself to and that would have worked in the master database. change myself to the AdventureWorks LT database. And I'm going to create a table called salesLT.employee, which has the employee ID, the employee name, and the manager, which is an integer ID that I'm going to use. So we'll go ahead and execute that. I'm then going to insert some data. We're going to cover inserts later on in this course, so don't worry too much about it. But I'm taking some data from the existing customers table. We have salesperson in there. So I'm going to grab the salesperson from the customers table, and I'm going to pour a bunch of them into the employee table I've just created. Then I'm going to do some updates, and effectively all of this is doing is ending up with a bunch of employees that have managers that ultimately they report to. So if I go ahead and do all of that, and let's not worry too much about the details of that, let's actually just have a quick look and see what's in there. So if I do a quick select, star from salesLT.employee. So you can see that I've got each employee has a unique ID and their name, and then the manager ID references the employee ID. So employee number 1 is managed by employee number 8. Employee number 2 is managed by employee number 1. And the only one who doesn't have a manager, the person at the top of the pyramid, is employee number 3. So we're able to see how that works, and that's typically how you might organize your organization chart. To find out who reports to who and to get some sort of details about that organization, I can use a self-join. So I'm getting the employee name from the employee table and the employee name from another copy of that table, which I'm using to represent managers as the manager name. I'm using a left join to join my employees.
So why have you used a left join there?
Because I'm going to have some employees who don't have managers. Or at least I'm going to have one employee who doesn't have a manager.
Top of the tree one.
Top of the tree is I want to include him. So I bring him out. He doesn't have a manager ID, but I still want to include him. And I'm joining it on the E manager ID equals the M employee ID. So referencing across to the same table. And if I go ahead and run that, and I actually get the employee name and the name of their manager, and I can see that that employee doesn't have a manager, and then I can see the name of the manager for each of the others. So that's a case where a self-join is a useful thing to be able to do. It's just the same as any other type of join, except that you have to use aliases because you've got the same table referenced multiple times. So that's the end of our module on joins and querying multiple tables. It's a fairly commonly done thing when you're working with databases is to use joins to query multiple tables. Sometimes there'll be inner joins, quite a lot of the time there'll be inner joins actually. Sometimes there'll be outer joins, and sometimes there'll be combinations of inner and outer joins, and that's when you have to be careful about the order. It's pretty much the only time you have to worry about the order that you specify the clauses in. Cross joins we talked about, bringing back the Cartesian product. Again, just to emphasize, it's not something you'll do a lot, but it's good to be aware of that ability to bring back every possible combination. And self joins, just like any other join, except that the tables you're joining together, it's the same table with different aliases to get back self-referencing data. So hopefully you've found that module useful. Please go away and do the lab, have a crack at doing that lab. And it again will challenge you to create multiple queries that have joins from various different tables, and will challenge you to do different types of join. See how you get on with that. There are some solution files provided so you can check your answers. And when you're comfortable and happy that you understand how you're using joins in Transact-SQL, come back and join us for the next module where we'll look at a different way of bringing multiple sets of results together when we look at using union to bring together different sets of data.